Okay, I'm going to show you an example problem using calorimetry. So here's the problem. I put 100 grams of ice at negative 20 degrees C into an insulated cup containing 300 grams of water at 25 degrees C. When the system reaches thermal equilibrium, what will the final temperature be and how much ice will be left? Okay, so we're assuming that no heat flows into the cup or into the atmosphere, that this ice-water system is a closed system, so that all of the heat that flows out of the water must flow into the ice. They must equal each other, right? That's my presumption. So, with that presumption, I'm going to do my calorimetry, but it turns out there's 4 possible things that happen, and the way that I do my equations depends on which one I think is going to happen. Either some of the ice melts, all of the ice melts, some of the water freezes, or all of the water freezes, all right? So I'm going to pick one of those scenarios, try it, and see if it works. If it isn't consistent, then I'll try another one. But I can make an educated guess. If I look at this, there's 3 times as much water as there is ice. They're both kind of similar temperature differences away from 0, right? The water's 25 degrees above 0, and the ice is 20 degrees below. So there's similar temperature changes to get them to 0 degrees C, just in opposite directions. But I have 3 times as much water, and the specific heat of water is about twice what it is for the ice. So that's like 6 times as much energy is released bringing the water down to 0 degrees as it takes to bring the ice up to 0 degrees. So I'm probably not going to be freezing any water. I can say that right now. I'm not going to be freezing any water. I'm going to be melting ice. It's only a question of whether I melt some of it or all of it. But we're going to work through all 4 scenarios just so that you can get an idea of how this works. All right? So let's first assume that I melt some ice. So I'm going to try one of these 4 scenarios. I'm just going to choose melting some ice. And it seemed like a good guess that we're not going to freeze water. So this is maybe a good one to try. The other good one to try starting off is I melt all the ice. All right? So let's write down our equation. And the equation is going to basically just be conservation of energy. Whatever heat flows out of the water must flow into the ice because it's a closed system. But I don't like to think in terms of heat flowing out of the water and into the ice because I'm more likely to make a sign error, I find, when I do that. So I have a system I use. I just pretend like heat is flowing into everything. In the case of the water, right, the water's cooling down, so heat must be flowing out. That's just a negative heat flowing in. So I'm going to think in terms of the heat flowing into the ice plus the heat flowing into the water must be 0, right? So one of them has to be positive, one needs to be negative. And so I like to do that. I just always think in terms of heat flowing into something. So what I'm going to do is I'm going to first find the heat flowing into the ice. So if I'm going to melt some of the ice, the first thing I've got to do is raise the temperature of the ice up to 0 degrees C. How much heat flows into the ice when I raise it to 0 degrees C? That's just the mass of the ice times the specific heat of ice times the temperature change. So how much the temperature increased? So to heat it up to 0 degrees C, my final temperature is 0 degrees C. My initial temperature is the initial temperature of ice. And that's how much heat it takes to bring my ice up to 0 degrees C. Once I get to 0 degrees C, I'm going to melt some of the ice, all right? So to melt a mass of ice delta M, I have to put heat into the ice, an amount equal to the change in the mass of the ice, how much I melted, times L, the latent heat of fusion, all right? Once I've melted the ice, I'm done, right? Because I'm assuming I'm only melting some of the ice. That means that when I'm done, I have some ice left in equilibrium with water. The only way that can be true is if the final temperature is 0 degrees C, because that's the temperature at which I can have water and ice in equilibrium with each other. So that's the heat that flows into the ice. I heat it up to 0 degrees C, then I use some heat to melt some of the ice and turn it into water. All right, now I'm going to consider the heat flowing into the water, right? I'm always thinking in. I'm adding all the heat that flows into everything, and it should add up to 0. The water, since it's actually cooling down, I should have heat flowing out of it, so the heat flowing in should be negative. Well, I use the same just pattern. Mass of the water, specific heat of the water, temperature final minus temperature initial. The final temperature is 0 degrees C minus the initial temperature of the water. That's how much heat flows into the water. It will be negative because really heat's flowing out of the water. All right, it's just final minus initial. And the final temperature, we already decided it has to be 0 degrees C. Otherwise, I can't have water in equilibrium with ice. So I add the heat that flows into the ice plus the heat that flows into the water, and that better add up to 0, right? This is Not so hard to do with ice and water, but if you have a system where you have multiple things, maybe I had 4 things coming into equilibrium, you know, which one's going to heat up, which one's going to cool down, I don't know. Just use the heat that flows into each of them. Make some assumptions. Some of this is going to melt, you know, maybe the other one's, maybe my third object is aluminum and I know it's not going to melt, all right? So just add up the heat of everything flowing in and set it equal to 0. All right. Now I know I'm presuming the final temperature, so now I just need to know how much ice melts. All right. So I solve this. First, I'll leave this term on this side and move the other ones to the other side. So I've got mass of the ice times the latent heat is equal to, and you know what? Since these are zeros, I'm going to throw them away. Now, if I'd used Kelvin, I wouldn't have 0 here and I couldn't throw it away. That's one of the nice things about using the degree C. Am I allowed to use Celsius rather than Kelvin? Yes, because we're only doing temperature differences. When I'm doing temperature differences, the difference I get in Celsius is the same as if I used Kelvin. I could have converted this to 273.15 Kelvin and done this all in Kelvin and gotten my answer in Kelvin. But if I'm happy getting my answer in Celsius, I can just use the temperature differences. This is 0. I can throw it away. And then what I have on the other side here is mass of the ice, specific heat of ice, initial temperature of ice, plus mass of the water, specific heat of the water, times the initial temperature of the water. I divide by L, and I get delta M is equal to mass of the ice, specific heat of ice, initial temperature of ice, plus mass of the water, specific heat of the water, temperature of the water, divided by the latent heat. Now, before I plug numbers in, I'm going to look at this and say, does this equation make sense? What does this equation really mean? Well, look at this. This is the amount of energy, right? I dropped the 0 degree C. This is just the amount of energy I have to, well, this is since I moved it to the other side of the equation, now it's no longer the heat flowing in, right? I multiplied it by -1 to move it to the other side. This is the amount of heat that flows out. This is the amount of heat that flows out of my ice as I bring my ice's temperature up to 0 degrees C. All right, and it will be a negative number because my initial temperature of ice is negative. So this is the heat that comes out of the ice, getting it to 0 degrees C. This is the heat that flows out of the water, getting it to 0 degrees C. This one's positive. I add them together, and that's kind of the energy left over after getting those two to 0 degrees C. If I take the energy left over, that's the energy I have to melt ice. If I divide by the latent heat, I can get the mass of ice I melted. So I almost could have written this equation down starting right here. But, you know, it's more intuitive to write it this way. But I can check my answer. I can look at it and say, wow, it totally makes sense. If I make the temperature of ice colder, bring this down, then I have less energy left over to melt ice, and that makes sense, right? If I made the initial temperature of the water higher, I'll have more energy left over, I can melt more ice. If I had initially more water, I'd have more energy to melt more ice, right? So you can see, if my latent heat is bigger, I'm going to melt less ice. So everything kind of scales the way it should. I know that this is an energy, right? This is an energy. This is energy per unit mass. So this is going to give me mass. It's going to give me the right units. I'm checking this out, and it seems like it makes sense. So I'm pretty confident I've got the right answer. So now I'm ready to plug numbers in. So the change in ice is going to be, the mass of the ice was 0.3 kilograms. The specific heat of ice, it's 4186 joules per kilogram Kelvin. If you look in your book, it gives it as degrees C. Same units, right? Because I always multiply specific heat by a temperature difference, and that's the same in Kelvin and Celsius. So instead of writing this as Celsius, I wrote it as Kelvin, but it's exactly the same because we always use this with a temperature difference, and it was easier to write this because then I didn't have to click and find the degree C symbol in the math library. Okay, then I multiply by the initial temperature, which is minus 20 degrees C. All right, once again, degrees C and Kelvin are different things, but because we're only doing temperature differences, they have the same difference, and I can cancel them. All right, for the water, we have, oh, sorry, this is the ice. This is the water, the ice. Okay, I'm going to move this one over here, and for the water, it's positive 25 degrees C. Sorry, I looked up the mass of the water and the specific heat of water and put it here. So for the ice, I have 1 kilogram, so this is really this term right there, and this is plus 25 degrees C. For the ice, I have 1 kilogram. The specific heat is 2090 joules per kilogram Kelvin, or degrees C, and my initial temperature of the ice is minus 20 degrees C. So the degrees C cancels again with the Kelvin here. And then in the denominator, we have the latent heat of fusion, which is 3.33 times 10 to the 5th, times 10 to the 5th, and the units are joules per kilogram. So, this kilogram can cancel that kilogram, this kilogram cancels this kilogram, and this joule cancels those 2 joules, and I'm left with 1 over kilograms, so the final answer I'm going to get is kilograms, right? I said my units were going to work out, and they did. So now I just need to get out my calculator and actually do this. And when I plug the numbers in, I've got, let's see, 0.3 times 4186 times 25. So that's going to be, let's come up here, 31,395. Plus, then I get the stuff for the ice, and it's going to be 0.1 times 2090 times negative 20, and I'm going to get negative 4180. All right, so if you look at this, the water, we predicted the water was going to give off, getting down to 0 degrees C, we said it would be about, we had 3 times as much water, so it would be about, and it's about twice, the specific heat is about twice as big as for ice. So we expected getting them to 0 degrees, the water is going to give off like 6 times as much heat as the ice absorbs. And it's sort of close, right? So 4 times 6 is going to be 24,000. We got 31, so it's close-ish. And then I'm going to divide this by 3.33 times 10 to the minus 5th, and my final units will be kilograms. All right, so if I do this, I'm going to take 31,395, subtract 41. My fingers are too big on this calculator. I apologize. Let me try this again. So 31,395 minus 4180. I know this is tedious. I'm not going to plug the numbers in every time. And then I divide that by 3.33 times 10 to the 5th. 10 to the, that's not minus 5, that's 10 to the 5th, right? Why did I write a minus 5 there? It's 10 to the 5th. All right. And that is going to equal, did I do this right? 0.0817 kilograms. Did I do that right? Let's see. So, yes, that looks like I did that right. So assuming I plugged the numbers in correctly, this is going to be 81.7 grams. How much ice did we start with? We started with 100. So this is reasonable. If we get a reasonable answer, then we must have chosen the right scenario, right? So I look at this and I say, my final temperature must be 0 degrees C, and my final, the amount of ice that melted, that's delta M, that's how much melted, so the amount left is going to be 100 grams minus this, 81.7 grams. But the point is, the amount of ice I melted was less than the amount of ice I started with, so I made the right choice. Now, had I done this and I found that the amount of ice that melted was more than the ice I started with, then I know I made a mistake, all right? And so if I find that I melted more ice than I started with, that tells me, oh, I must have melted all the ice, so now I need to try the all the ice melted scenario. If I did this and I got a negative amount of ice melted, that would tell me, oh, ice didn't melt, water must have froze. So we'll try one of the water freezing scenarios. So imagine that I'd gotten more than the amount of ice I started with. And we'll say, oh, that means that all of the ice melted. All right, so it looks like I've got the right answer. I tried the right scenario first. I made a good guess. But what if I tried this and I'd gotten that more than the total amount of ice melted? Then I say, oh, that means all the ice melted. So I'll try this technique. So I would try again. I would say all ice melted. And then my equation would look like this. So if I assume that all of the ice melted, what happens? Well, first of all, I've got to get my ice up to 0 degrees C. All right, so how much energy does it take to do that? Mass of ice, specific heat of ice. Final temperature is 0 degrees C. For this step, minus the initial temperature of the ice. After it's 0 degrees C, I've got to melt it all, but I'm going to melt all of it. So it's going to be not delta M, it's going to be all of the ice melted times the latent heat. Once I've melted all of the ice, I've got this water that used to be ice, and maybe it's still at 0 degrees C. It's at 0 degrees C, but as I pulled the heat out of the other water to melt the ice, maybe it's not all the way down to 0 degrees C yet, so it can give off more energy, and my ice is going to absorb more energy, which will raise its temperature. So the heat that it absorbs as it raises in temperature now is mass of ice, specific heat of water, temperature final minus 0 degrees C. So in this step, my ice is no longer ice, it's water, right? So I have this mass of stuff, but it's no longer ice anymore because I melted it in this step. So I'm going to use the specific heat of ice. As I heat up this stuff that used to be ice, it's now water, so the specific heat is the specific heat of water. And I'm not heating it from the initial temperature of ice. I already heated it at 0 degrees, melted it. Now I'm heating it from 0 degrees C up to the final temperature. That's the heat that flows into the ice. There's 3 steps. Heat up the ice to 0 degrees C, melt it, then heat up that water we melted up to the final temperature. Now if I look at the water that I started with, all right, how much heat flows into that? Mass water, specific heat of water, and it's just going to go directly to the final temperature from its initial temperature, right? Because it's not going through a phase change. And I set that equal to 0. Now notice I assumed something. I assumed in this scenario that all of the ice melted. So I'm assuming that the amount of ice left over at the end is 0, that the amount that melted is 100 grams, right, the amount I started with. So the one thing I have to find then is the final temperature. And as you can see, this is just algebra now. I solve for the final temperature. I'm not going to do that algebra, but I'm just going to say, imagine you get your final temperature, all right, you do all the checks like we did. Does it make sense? If I have more ice, the final temperature should be lower. If I have less ice, to start with, the final temperature should be higher. I check my units, I do all of that stuff, and I'm convinced my answer is correct. I plug my numbers in, and I get some final answer. All right? Now, let's assume that that final answer is hotter than the initial temperature of the water. If you get that, you just made a mistake. Your algebra is wrong. You plugged something into the equations wrong, right? You can't get something higher than the initial temperature of your hottest thing, right? But let's say that I got something which was lower than the initial temperature of the water, but higher than 0 degrees C. That's good, right? We're assuming that we have no ice left, so we have to be higher than 0 degrees C, or just right at 0 degrees C is also possible. I can have all water at 0 degrees C. So if my answer is somewhere between 0 degrees C, or actually at 0 degrees C, but less than the temperature, the initial temperature of the water, then I know I made the right choice and I've got a good answer. Well, assuming I did everything right. But if I find out that my temperature is below 0 degrees C, that tells me that either all of the ice didn't melt, or maybe even some or all of the water froze. So if my answer is between 0, my final temperature is somewhere between 0 degrees C and the initial temperature of the water, then that's an indication I chose the right scenario and I've got my answer. But if it turns out to be above the temperature of the water, I'm just screwy. I just did something wrong. If I get a final temperature below 0 degrees C, then that probably tells me that I chose the wrong scenario and not all of the ice melted. All right, so I can go back and try the not all of the ice melted, some ice melt scenario. Or maybe even some of the water froze. All right, so let's try the some of the water froze scenario. Some water froze. So for that scenario, what heat flows into the ice? Well, if some water freezes, that means none of the ice is melting. So I'm just taking my ice from its initial temperature to its final temperature. So the heat that flows into the ice is just mass of the ice, specific heat of ice, final temperature, minus the initial temperature of the ice, all right? And the ice, so if some of the water freezes, all right, if some water freezes, what does that tell me? I haven't froze all of the water. That means I have ice and water in equilibrium. That means my final temperature is 0 degrees C. So I shouldn't put temperature final here. I should put 0 degrees C, all right? And that's how much heat it takes to warm up my ice to 0 degrees C. That's all the energy that flows into my ice, because I'm not melting any of my ice, I'm freezing water. Okay, so how much heat flows into the water? Well, first I have to cool the water down to 0 degrees C. All right, so that's how much heat flows into the water. And notice it will be a negative amount of water, of heat flowing in, because it starts out above 0 degrees C. So some heat flows out of the water, that's negative heat flowing into the water. That gets the water to 0 degrees C. Once it's 0 degrees C, I'm going to freeze some mass of it. Remember, this is heat flowing into the water. Heat flowing in does not freeze ice. It freezes water, it melts ice, right? So this is going to be a negative heat flowing into the water, negative delta M times L, where delta M is the amount of water that we freeze into ice. All right? And that should all add up to 0, right? I cool the water down and then I freeze some of it, and I'm done. All right, so now I'm assuming that the temperature is 0 degrees C because I have ice and water in equilibrium. I solve this for delta M. If the amount of water that I freeze is somewhere between 0 grams and the amount of water that I started with, right, which in this case was 300 grams, if it's somewhere in between there, then I probably chose the right approach, and I've got my answer. But if I find that I froze a negative amount of water, then I chose the wrong thing. That means that some or all of the ice must have melted, right? If, however, if I find a negative amount of frozen water, I actually melted ice is what happened. I want to try one of the other scenarios, 2 scenarios we already tried. If I find that the amount of ice I melted is greater than 300 grams, then I chose the wrong scenario because I chose that only some of the water frozes. Obviously, all of it must have froze because I can't freeze more than 300 grams. So if I find that delta M is greater than 300 grams, greater than the mass I started with, I'm going to try my 4th scenario. I'm going to throw that away and go back and say, no, what must have happened is all water froze. All right, so for this scenario, if all of the water freezes, then my final temperature is going to be 0 degrees C or lower, right? Because if all of my water freezes, I'm just left with ice in the end, and that can't be above 0 degrees C. So I don't know my final temperature, but I do know that the amount I melted, the amount of water that I froze is 300 grams, right? I melted all the water. So I know that. I know I'm left with no water. My total ice left is going to be the mass of the water plus the mass of the ice I started with, right? So I know I melt. In this scenario, I'm assuming I freeze all the water. I know how much ice I'm left with, but I don't know the final temperature. So let's do our heat equation. So my ice, how much heat does it absorb? Mass ice, specific heat of ice. And the ice now is going to go right to the final temperature, all right? And it's going to be something 0 degrees C or lower, and that's it. That's all the heat that my ice absorbs. How much heat does the water absorb? Mass of water, specific heat of water. First, I've got to get the water down to 0 degrees C before I can freeze it. So final temperature 0 degrees C minus the initial temperature of the water. So that's the heat that flows into the water to cool it to 0 degrees C, and it will be negative because really cooling the water to 0 degrees C means heat flowing out of it, right? So it's a negative heat flowing in. And then I'm going to have some more negative heat flow in. Heat's going to flow out as I freeze all of the water, all right? And this is how much heat, without the minus sign, this is how much heat flows out to freeze the water. With the minus sign, then it's like that's how much heat flows into the, and this negative amount of heat flows into the water to freeze the ice. Once the water is all frozen to ice, then the water can continue to cool down. How much heat flows into the water as it cools down now? Well, it's mass of water, but now it's ice. I've frozen it, so I use the specific heat of ice. I'm going to go to my final temperature from 0 degrees C. And my final temperature will be negative, right? So this is once again going to be a negative heat flowing into the water because it's actually heat flowing out as this thing cools down. And all that adds up to 0. So I heat up the ice. There's some heat that flows out of the water, negative heat flowing into the water to get it to 0 degrees C. There's some heat to freeze all the water, and then there's some heat to continue cooling the water down to its final temperature. So I'm going to solve this equation, right? All I have to solve for is the final temperature. What do I expect the final temperature to be? I expect the final temperature to be less than or equal to, I expect the final temperature to be less than or equal to 0 degrees C. If it's higher than 0 degrees C, I couldn't have melted all the water. Or she couldn't have frozen all the water. There must be some liquid water left, all right? So if I find an answer which is less than 0 degrees C, then I probably chose the right scenario. If my final temperature is lower than the initial temperature of the ice, I made a huge mistake, all right? I made some algebra error, plugged something into my calculator wrong. But if I do my algebra right and I plug everything into my calculator properly, then I should get an answer which is somewhere between the initial temperature of the water and the initial temperature of the ice. If I find that my answer is greater than 0 degrees C, then I assume, oh, all of the water must not have frozen. I better go try one of the other 3 scenarios. But if I get something below 0 degrees C, then and I did everything right, that means I chose the right scenario and I've got my answer. And that's all I have for you today.